Thank you. I hope that you enjoyed your meet yesterday evening. We only couldn't have a pizza because the kitchen was too busy, but at least I hope you enjoyed your meet. So this is the last lecture because this afternoon will be devoted to your questions. So please collect all these questions and I will try and answer them. Uh, we were discussing the construction of the effective Lagrangian involving nucleons. We concentrated in the previous lectures on the effective Lagrangian involving only pions. For the sake of derivation of nuclear forces, it's important, of course, to include nucleons. And appropriate choice for the nucleon fields, which is a doublet, an SU2 doublet, containing a proton and neutron, was to dress it with pion Goldstone bosons such that the transformation properties under a chiral local chiral group was simply this one in terms of this SU2 transformation H, which is the compensator field. This H also appear in the transformation of the Goldstone boson matrix, actually the square root of the Goldstone boson matrix, in this way. U V L dagger, and this is equal to V R U H dagger, and of course the Hermitian conjugate is H U dagger V R cross, and then it is equal to V L U cross H cross. And in this way, there are no non-derivative coupling with the pions. For example, the mass term, the nucleon mass term, which of course must be part of the effective Lagrangian, will not involve the pions. Of course, this is invariant because if this goes into NH H cross, and this goes to H N, no matter what the chiralities are, and then since this is a SU2 matrix is identity matrix and this is invariant, and does not involve the pion field. The pion field is put into the definition of the nucleons. But there also can be a derivative interaction, of course. And derivative interaction, notice that we cannot form invariants like that with the appropriate, perhaps, factor of gamma matrices in order to produce a Lorentz scalar and parity invariant operator. Because this transform like VR d mu VL dagger. This transform like N dagger H cross, and this transform like H N. So there is no compensation in these two terms. It's not invariant. But we can produce an invariant operator, a covariant combination like that. U cross d mu U cross. Under chiral symmetry, U cross goes into this H, U cross V R dagger, then this is covariant derivatives. V R d mu U V L dagger, and then U cross, I take this second expression, V L U cross H cross. So we are happy because this is identity matrix, and this is also identity matrix, so that the transformed goes into this way. H bar. So it transforms covariantly with these appropriate factors. so that we can form, okay, it is convenient to define a field in this way. Let us call it U mu with the Lorentz index, which is this Lorentz index from the derivative. Okay, we define like that. And also, in order to have a Hermitian conjugate operator, we multiply by I, otherwise it is anti-Hermitian. Okay, so this operator, this is a building block, you see, because we can combine N and this U mu to form interactions between pions and nucleons. A term like that, N bar, then U mu N, under the chiral symmetry, it transforms, it is invariant because it goes into N bar H cross from this. Then this transform covariantly U mu H cross, and then the nucleon field, another factor of H N. So this is factors are unity, and we have an invariant operator under the chiral symmetry. Of course, this is not possible in a Lagrangian because it is not a scalar under Lorentz. So we have to saturate somehow this Lorentz index mu. And this is why we multiply by this gamma matrix mu. We could also insert further derivatives, but you remember, the more derivatives you include, the more suppressed will be this term at low energy. So we insert here a factor gamma mu, which doesn't cost any factor of momenta, of small momenta. Okay, so this is Lorentz scalar, could be part of a Lagrangian, but it violates parity. Remember that pions are pseudoscalar. They change sign under parity, not like scalars, which are invariant under parity at the mirror. Pseudoscalar change sign. And so we, to respect parity, which is a symmetry of the underlying theory of strong interactions, nobody knows why, but parity is a symmetry of the strong interaction. Nobody has solved the so-called strong CP problem, but we take it as a fact of nature, of experiment, that parity is a good symmetry of the strong interactions. Therefore, we have to respect also at the effective level, in the effective Lagrangian, and we are obliged to put this gamma matrix, gamma 5, okay? So the coupling of this term is of axial type. In the effective Lagrangian, we are allowed to consider terms like that. Gamma 5, U mu, psi, N. Okay, this is a appropriate term, part of the effective Lagrangian, because it is chiral invariant, Lorentz scalar, invariant under parity. It will be accompanied by a low energy constant, okay? And this low energy constant is called GA. It is nothing else than the axial coupling of the nucleon. Axial coupling of the nucleon. We already met this constant when we spoke about the Goldberger-Treiman relation. Why this is the axial coupling of the nucleon? Well, you can do it as an exercise, because it is precisely the constants which parameterize the coupling of the nucleon with external axial current. Where is the external axial current here? Doesn't seem to be present, but it is present here inside U mu, okay? Remember that in this covariant derivative of the pion field, there are also external current, okay? We have wrote the explicit expression for the covariant derivative of the pion field last time, and it had the right current at the left and the left current on the right, as usual. Okay, so axial current is the combination R minus L, so it is present here. Okay, so this is why the low energy constant is dictated, no, by the coupling of the nucleons with the axial current. Coupling of the nucleon with the axial current is the same as the coupling of the nucleon with the pions. This is another, a modern way to express the famous PCAC relation, when one substitute the pion field with the divergent of the axial current. This is the same thing, okay? Or compact notation for this is 1/2 GA n bar u slash gamma 5 n. This is an allowed coupling of pions with nucleons. Where are the pions? I discussed very briefly where are the currents, external currents. Pions are, so I remember the building block was this. At the extremes there are lowercase u, and in the center uppercase, okay? So these are the square root. You could wonder, you could verify that also this combination is covariant, okay? This also goes like under chiral symmetry, like u d mu u cross lowercase h dagger. But it's the same. It's the same as you can express using the unitarity of the U matrix. You can express this in terms of this, okay, as an exercise. So it's not an additional building block. It is always the same. There is only one U mu, okay, which comes from the covariant derivative of U or covariant derivative of U cross. Okay. So where are the pions here? The pions are in these matrices. U, for instance, was e to the I pi a tau a over f. You remember? How do you understand the exponential of a matrix? As its Taylor expansion. I pi a tau a over f plus terms with 2 powers of pion field and so on. Okay? So d mu u, which is contained in this covariant derivative, in the absence of the external currents, covariant derivative is the same as ordinary derivative. D mu u is something like I over f d mu pi a tau a plus terms with 2 powers of pion fields. Then in the expression of u mu, there are also this lowercase u dagger. Okay, what is u dagger? It is the derivative, the square root of capital U dagger. So it is the square root of e to the minus I pi a tau a over f. So it is e to the minus I pi a tau a over twice f. Like that. What is it? The exponential of a matrix. It's Taylor expansion. Identity minus I pi a tau a over twice f plus terms of order p square. So you see that this building block u mu is equal in terms of the pion fields, is already at least linear in the pion fields, you see, because there is a derivative acting on this u, capital U, when there are no pions, is simply 0, okay? So it is at least linear in the pion fields. And so we don't need to consider the sub-leading terms in the lowercase u dagger here. And the u mu, we can simply multiply this by I to get minus 1 over f d mu pi a tau a. This is the expression of this building block, u mu, in terms of the pion fields. It starts with the linear term, then coupling with more pions. Okay? A derivative of pion fields. So this reflects the characteristic of the interactions pion and nucleons, which are derivative interaction. Therefore, this term in the effective Lagrangian, 1/2 GA n bar gamma mu gamma 5 u mu, put lowercase here, u mu n is equal to 1/2 GA n bar gamma mu gamma 5. Substitute in terms of this, put a sign, minus sign here and f sign here, and then here we have d mu pi a tau a n. So this is the coupling with plus terms coupling nucleons with more pions, more than one pion, okay? More complicated vertices. Gamma mu, do you remember the expression for gamma mu? Dirac gamma matrix. There are various representation of the gamma matrices. The most widely used is the, I don't remember the name, the one for which the temporal part gamma 0 is diagonal. And here we have the Pauli matrices, okay, like that. Pauli matrices we always have denoted by tau. Okay? Here we denote it by sigma because they have to do with spin. This kind of Pauli matrix has to do with isospin, so it is common to differentiate the notation. Okay, when talking about spin, they are called sigma. Isospin, they are called tau. So, and gamma 5 in this representation, I recall that gamma 5 is this, 1, 2, 3, and this is a non-diagonal matrix, which, okay, makes the large component and the small component of the Dirac spinors. So you see that if this mu is temporal, if mu is equal to 0, this gamma structure is gamma 0, gamma 5, gamma 0, gamma 5. And gamma 0, gamma 5 is nothing that 0, 1, minus 1, 0. So it's a matrix which mixes the large and small component of the spinors appearing in the expression of the nucleon fields. Okay, remember, large, small component have additional factors of momenta, of soft momenta in this case. So they will contribute at higher order. The most important part will come from the case in which this Lorentz Dix is space-like. Mu is equal to I. Okay, so mix with small components. Small components. So this we can disregard. Instead, we have the case when mu is equal to the temporal I, temporal index I. In this case, so this combination of gamma matrix, gamma I, gamma 5, is simply the sigma 0, 0 minus sigma. It's a diagonal matrix. Okay, it doesn't mix large and small component. In particular, it contributes, large components contribute. Okay, this is the sub-block, 2 by 2 sub-block. So this is the sigma, the spin matrix. And the non-relativistic reduction of this term in the effective Lagrangian is the coupling constants GA over twice F, then, and then there is N, okay, N, okay, I'm mixing the notation here, N dagger, then sigma, then the space-like, okay, the space-like for derivative, which is the gradient of what? Of pion fields, tau matrix, N, okay? So this is a coupling of nucleons with pions of derivative type. Diagrammatically, is a coupling like that. This is the nucleon and this is the pion, Okay, is a cubic vertex like that. Convention is that nucleon lines are continuous and pion lines are dotted, dashed. Okay. This in this n, I'm a little bit misleading here, but I don't want to enter into too many details. These are n fields. They became the Pauli spinors. Okay, Pauli spinors. The non-relativistic expansion of the Dirac spinor. Okay, only the large components are involved at the lowest energy. So this is the pion nucleon coupling, which has this low energy constant Ga over 2F, where F is the pion decay constant. Of course, adding more and more powers of these building blocks, we can construct more and more complex terms in the effective line. There will be an infinity of them, but they will involve more derivatives, and then will be more suppressed. These terms only involve one derivatives, so it is part of the Lagrangian, let's say, L1, okay? This is the index, the chiral index, if you like, of this Lagrangian. And people denote this Lagrangian with pi n. Is first order, is part of the first order pion nucleon effective Lagrangian. It contains this coupling with the nucleon, with the pion, okay, which is of axial vector type. It's not pseudoscalar type, okay, which would not involve the derivative because we have changed the nucleon field accordingly. Then there will be other building blocks. For instance, involving the scalar pseudoscalar source chi. You remember this chi under the chiral symmetry was transformed like that, chi VL dagger. Okay, so if you multiply this chi with with U dagger, chi U dagger under the chiral symmetry, it goes like U H U dagger VR dagger, then transformation of chi VR chi VL dagger, and then transformation of U cross. I take the last expression VL U dagger H cross, and this is was done on purpose to have identity matrix. So these building blocks, you see, this building block transform covariantly, let's say. So it can be put inside a fermion bilinear. Okay, so for instance, a legitimate term would be U dagger chi, U dagger n. Okay, this is invariant under the chiral symmetry. Invariant under the chiral symmetry because it's like before. Another building block is U chi dagger U. Actually, it is necessary to add both terms because of reality of Lagrangian. So, and so on. Also, there are building blocks involving external sources like R mu nu. Remember, this is the curvature associated to the external sources. R mu nu went like that under the chiral symmetry. R mu nu VR dagger. VR dagger. So we can combine this curvature with appropriate factor of Goldson bosons, such that, for instance, if you multiply by U dagger to the left and to U to the right, you discover that it is covariant. And very similarly for the external source, for the left sources. Okay, so this is the way to consider all possible building blocks in the effective Lagrangian. They will involve either derivatives of the pion fields in the form of this field U mu, okay, which contains a derivative, or factors of this external source chi in this way, which also is a small quantity, because remember chi in the counting contains the quark masses. So also these are small effects. Okay, the more factors of chi you include, the more will be this index in the effective Lagrangian. You can forget in the first instance. Okay. Also, the external sources, you see here, it's also order p square, the counting of the external source, as we saw yesterday, because it involves two derivatives, and then or one derivatives and one external source, so two powers of small momenta. So, for instance, they will not appear in the L1. Okay. There is another building block which is important to realize. So here I can erase this. The derivatives of nucleon fields. But here we have to pay attention, because derivative of nucleon fields under the chiral symmetry, uh, it gets a contribution, an unwanted contribution. You see, it does not transform simply by multiplication with this H, we say covariantly, but involves the derivative of this compensator field H. How do we manage then? In the usual way, by replacing the derivative, simple derivative, with a covariant derivative. Like we did for the pion. It was this capital D, okay, capital D. We have here a covariant derivative for the nucleons, not a covariant derivative for the pions, but for the nucleons. Usually, people use the same notation. Well, let me not do that, okay? To differentiate between covariant derivatives of the nucleons, lowercase d, and covariant derivative of pions, uppercase d, okay? And this is the simply the addition of to the derivatives of some, like a gauge field, okay, of a connection, would say the mathematician, gamma mu, such that this gamma mu compensate this unwanted term. It means that under the chiral symmetry, it must go in the following way, like H gamma mu H cross minus d mu H cross, like we saw for the external sources when we talk about Goldstone bosons. So we have to add a derivative, this connection, gamma mu, and build in this way a covariant derivative, d mu, for the nucleon fields, such that d mu of the nucleon fields under the chiral symmetry goes simply like H d mu. Okay, this term compensate the unwanted term like that. Okay, so where is this gamma mu? Gamma mu which transform in this way under the chiral symmetry. We have to build it somehow, and let me do that in this blackboard. Okay, let me start from this transformation of this lowercase u, which is written here. Under the chiral symmetry, I must differentiate all these three factors. So I have three factors, goes into d mu h u v l dagger plus h d mu u v l dagger plus h u d mu v l dagger. Okay, so it is almost so it is right that it involves derivatives of the compensator fields, which appears here, but not exactly in the form that we need it. But we can multiply by u dagger like that and use this expression to obtain the transformation of this combination is the one above times this transformation of H of U cross, okay, which I wrote, I take the second expression via U cross H dagger. So in this way, we discover the following thing, that d mu U dagger goes into, you see, these terms will cancel these terms and we stay with d mu H dagger, okay. This resembles what we need, okay. Then we have another contribution which is homogeneous, let's say d mu U dagger H dagger from this, and then we have an extra contribution H U d mu VL dagger VL U dagger H dagger. Okay, so we are almost there. Then also we can verify that d mu U dagger, so there is this unwanted term, which we can rearrange using the unitarity in this way. If you remember what we did about the external sources, this could be compensated by the inclusion of the external sources, because this term is part of the transformation law of the external left source. Okay, so instead, this combination, okay, this other combination will involve the derivative of this U dagger, which is d mu H U dagger VR cross plus H d mu U dagger VR cross plus H U dagger derivatives of VR cross. And I have to multiply by U. I take this expression for U VR U H cross. And this is given now by, you see, this is VR. VR cross is the unity. Also, then we have U cross U, which is unity. So I stay with d mu H dagger, like the one above. Then I have a homogeneous term, H d mu U cross U H dagger. And then I have a term involving the derivative of the right SU2 transformation. So which I can put in the same form as above, U dagger VR dagger d mu VR U dagger H dagger. Okay, so let me erase this. So these covariant derivatives is given in the following way. I can add this term, these two terms, and add appropriate factors of the external sources. So to compensate this, the one which arose here. But I have to take the sum and then half, okay, because I will have double what I need. So this, and I should change sign because I want transformation with minus sign. Well, I get the transformation with the plus sign. So I have to make minus 1/2 and then d mu U dagger plus d mu U dagger U, and then I have to include factors of the sources I U cross R mu U plus I U L mu U cross. Okay, if you combine all these ingredients together, that is to say, if you understand the transformation properties of the terms that I have added, you will see that they will cancel these unwanted terms here. So that is an appropriate choice for the for this gamma mu. This is called the chiral connection. The chiral connection. Okay, there are the pion fields here. You see through this matrix U. So they are dynamical terms. Okay, so usually one you see this is this term here is minus U cross d mu U, because okay, they are unitary matrices. So you have that U cross U is equal to unity, and the derivative of this gives the relation that you can write this term like that. So you have the commutator 1/2 commutator of U d mu U plus terms involving the sources U dagger R mu U minus I over 2 U L mu U dagger. Okay, this is the chiral connection. If we replace ordinary derivatives of the nucleon fields by this covariant derivative of the nucleon field, then we have covariant terms, transforming like that. D mu over of the nucleons goes into H times, okay, this thing. So another term in the effective Lagrangian, the kinetic term will be like that. D slash minus M nucleon N. Okay, this is a term of the effective Lagrangian. The mass term we have already discussed. Is not very interesting because it does not involve the pions. This is the one that we just constructed. It is a kinetic term for the nucleons and contributes to the Dirac-Lagrangian of the nucleon fields. Plus, there are interactions through the chiral connection. Okay? So, the Lagrangian, the complete Lagrangian, can be written like that. Okay, so this is the complete Lagrangian at lowest order. Pion nucleon Lagrangian at lowest order 1. Why? Because there are no more terms. You could wonder, there is also this possibility of term, you know, which is invariant. A term not involving pions, and the trace of this field U. Remember that this field U under chiral transformation went like that. So it is transformed in this homogeneous way. If you trace it, flavor trace it, then this H you can replace, then you can shift, and you have, this is invariant. So apparently this is an additional term, different from this, okay? But this is 0. You can check by exercise that unitarity of the Goldstone boson matrix gives this, that this is 0, okay? So this is the most complete Lagrangian with order 1. What is this 1? Simply it counts the number of derivatives, okay? Number of derivatives, one is inside is U, which has a Lorentz index, U mu contracted with the gamma matrix, and another is here in this chiral covariant derivative of the nucleons. And it involves also the pions. For instance, gamma mu, you see, we can discover that this chiral connection contains interactions with the pions. Before the break, let's do that and understand what is inside this gamma mu, this chiral connection gamma mu, in terms of pions. Pions are inside these U matrices. Okay, so we have to expand those matrices and find the simplest term involving the pions. Let's do that in the absence of the sources. So ignore, okay, external right or left sources. So concentrate on this term. I recall that the U dagger was e to the I minus pi a tau a over twice f, twice because it is square root, okay, minus because it is U dagger. And the U was e to the plus I over 2f pi a tau a. Okay, so this d mu u is at least linear in the pion field. Yes, I have already used these formulas. So we have to make the following calculation. 1/2 is gamma mu is equal to 1/2. Then U dagger, this is commutator of U dagger, that is to say identity minus I pi a tau a over twice f with derivative of this u, okay? So the derivative d mu of identity plus I over twice f pi, let's change the notation for the, yes, please. The sources, yes, because we consider the coupling of the pions with the nucleons, not with the external. This would be, you might ask, what is the use of these external sources in practice, physically? Remember that these external sources, they represent the coupling in the QCD Lagrangian with the left-handed quark currents. For instance, this source L mu was the term, additional term that we inserted in the QCD Lagrangian, which was like that: psi bar left tau a over 2 L mu a psi L. This was one of the terms that we had in the effective Lagrange. We did this for a trick to compute the QCD correlation function. It sounds like abstract thing, but in fact, a term like that, it exists in nature, outside of the strong interaction. Okay, they are the weak currents. Okay, the ones. This could be, for instance, the fields of the W bosons. Okay, so if you would consider beta decay involving exchange of a W, then this would be okay important. Okay, otherwise, if one is not interested in that, then to understand the interactions of the pions with the nucleons, okay, forgetting about weak effects, okay, which are weak, so we can understand, we can neglect, then we can do this approximation, okay. And then we have to, okay, so this commutator, derivative of a unity matrix is 0, so this is I over twice f d mu pi b tau b. Okay, so in this gamma mu, there are terms with perhaps at least one pion field, because this factor is at least linear. But this is 0 because the commutator of identity matrix with tau matrix is 0. Identity matrix commute with everything. So the linear term in the pions is 0. The first term is quadratic in the pions. Okay, from the commutator of this Pauli matrix tau A with this Pauli matrix tau B. So, okay, this commutator is 1/2. Then the numeric factor is minus I times plus I is 1 over 4f squared pi A pi B. These are not matrices, these are fields. And this commutator of tau A tau B, okay, which is twice I epsilon A B C tau C. And I forgot here that this pi B was the derivative of pi B. Okay? Otherwise, it would be 0, okay, because of symmetry. Okay, so this is the interaction included in this chiral connection gamma mu. In this gamma mu, there are terms involving no pions, also terms involving 2 pions, also terms involving 4 pions, arbitrary number, even by parity, okay? Even number of parity. So in the effective Lagrangian, the coupling of this nucleon from the kinetic term I gamma mu n, this is part of this kinetic term of the effective Lagrangian, it contains a coupling of pions and nucleons, 2 pions and nucleons. First of all, remember the gamma matrices. In this case, before, for this contribution, what was important was the space-like indices, mu. In this, because there was a gamma 5. Here there is no gamma 5. So the mu equals I mix large and small component. The largest term is mu equals 0. Okay, so this is gamma 0. And then this gamma mu is the temporal component. So this d mu, derivative of mu, is temporal derivative of pion fields. Okay, and at the end, we have that the coupling of the nucleons with the pions is the following. There is an I minus 1 over 4f squared epsilon ABC n dagger pi A d0 pi B tau C n. This is a coupling of the nucleons with the pions. 2 pions, okay? A derivative coupling, so it is a small number, is part of L1, okay? But it contains interaction of the nucleons with 2 pions, okay? Notice one important thing, that the coupling constant is not unknown. This is known. It is the pion decay constant, F. Okay, so this is some sort of a prediction of the framework. It must be a consequence of the word identity that we implicitly imposed by this formalism. It is called the Weinberg interaction, if I remember well. Weinberg, perhaps someone else, but Weinberg interaction. An interaction of nucleons with 2 pions. We are discussing the ingredients of these fields of this theory of pions and nucleons, okay? Which are used to please say it again. Yes, Mn, this is the nucleon mass. We can write it effective. Okay. effective mass, this is, to be precise, sometimes people call this mass of the nucleon Mn0, because to be precise, this is the mass of the nucleon in the chiral limit. Explicit chiral symmetry breaking effect are contained in these sources chi and so on, and in the low energy constants. Okay, but this limit of the nucleon mass in the chiral limit is not a small number, is very little different from the 940 MeV. Okay, so it's not a big change. But so I don't exactly know what do you mean by effective nucleon mass. It is the mass of these which are not protected by chiral symmetry. You see, because bar n is chiral invariant. Under a chiral symmetry, the fields, the mass is forbidden, but for the nucleons, which we chose to transform like that, it is because they are not Goldstone boson. Their mass is not protected by chiral symmetry. They can have a mass even in the chiral limit, and this is its value appearing in the Lagrangian. Okay, so since it is the time, we make a 5 minute 10 minutes break, and we resume at 10:05. Okay? Sharp, yes. Okay, let us start again. So we discussed the vertices, so to say. Okay, so we discussed all possible. Well, all possible. This is the Lagrangian at the lowest order. At the lowest order. Then there will be a Lagrangian at the next order that I don't remember by heart, but I can look at my notes. And then there is this Lagrangian L2, just to L2 Lagrangian. I must have written in the notes that I don't remember with the pion with the nucleons. Well, where is the okay? This is for instance. So if you want to know, the complete Lagrangian to second order in the chiral counting is the following, with the normally accepted convention, involves this plus chi cross u plus minus c2 over f m square u mu union d mu d mu d nu plus Hermitian conjugate plus c3 over 2 u mu plus I for c4 sigma mu nu commutator u mu nu plus twice b0 c5, then u chi cross u plus u cross chi u cross minus u cross chi plus chi cross u. Then there is another low energy constant called C6 over 8 times nucleon mass. Then there is a sigma mu nu, and this combination that we encountered, u plus u L mu nu u dagger, and then finally a seventh low energy constant, which is called C7, divided by 8 times nucleon mass sigma mu nu, and trace of R mu nu plus L mu nu n. Okay, this is the next to leading Lagrangian. We have written the subleading Lagrangian for the pions, And this is the subleading Lagrangian for the nucleon and pions. The index is 2. Why 2? Because there are two derivatives. For instance, here you see there are two powers of this field u, mu. Okay, so two derivatives. No derivatives in this term, but the presence of a source, scalar pseudoscalar source, which contains the quark masses. Quark masses, if you remember, should be counted like order p square by the Gell-Mann-Ox-Renner relation. Also here, twice order p square, order here, two powers of these fields. Here, again, presence of the quark masses. Here, presence of the external curvature, external source, also p square. Also, this is p square. And that's it. There are no more independent terms. All that is unknown at this order in the low momentum expansion is contained in these coefficients, C1 until C7. These are the low energy constants appearing in this L2. We don't know them. We could know them if we could solve the QCD, but we can take it from the experimental data. Okay, we take 7 observables and then use these observables to determine the value of these low energy constants to make predictions. Okay, there are not so many. Okay, there are 7. The more the accuracy you want, the more you consider powers of momenta, the more terms you would have, the more low energy constants to be fitted to data. Then, therefore, the predictivity is weaker if you want to increase the accuracy. Which processes you choose for determining these constants? For instance, this constant C6, it depends on the coupling, you see, with the external sources. For instance, electromagnetic field. Okay, we discussed about the weak, okay, external sources. If you can include the photons here in these external sources. So this would be the coupling with the photons, okay, of the nucleons, okay. Pauli term, to be precise. So this constant C6 is determined from the anomalous magnetic moment of the nucleons. And there are two combinations, proton and neutron, or if you like, isovector and scalar. So this is the way these constants can be determined. Okay. Then, after discussing these vertices, so these these interactions, we have to discuss loops. For instance, there was a loop here which contributed to the self-energy of the nucleons. It will contribute to the renormalization of the nucleon mass here. We can ask about the powers of momenta inside a general diagram involving loops, as we did for the Goldstone bosons sector. Okay, simply count the number of power of momenta. And so if there are L loops, each loops involve an integration of intermediate momentum, for instance here. So each loop brings 4 powers of soft momenta. Then there will be internal lines. Internal line, yes? Here, there is a good question. You say Hermitian conjugate. There is n. There is a parenthesis, big parenthesis here. So these derivatives act on this n. HC, Hermitian conjugate. No, this is okay. Plus Hermitian conjugate. Sloppy notation. I'm sorry. Hermitian conjugate. Otherwise, it's not automatically Hermitian. No, I thought that you were asking the question that here there are two derivatives, right? Two derivatives. And plus also these two. So you might wonder why this is of order L in L2 and not in L4. I thought that this was your question. And the answer would have been that when you take derivatives of the nucleon fields, which is a heavy fields, this is not suppressed, okay, in the chiral counting, because these derivatives could be temporal derivatives. When you derive the nucleon fields, temporal derivatives brings a factor of energy, including rest energy, which is not small. So derivatives of the pions are small quantities. Derivatives of the nucleons are not small quantities. That would have been the answer. Yes. 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 Yes, you're right. Yes, this is perfect. The status, what is this? Okay, there is progress. Quite slow, but there is progress. Since the time I began in this field, there has been a huge progress. So the simulations are bigger and bigger. You have to put the theory in a lattice, discretized space-time. And it's very difficult to put light quarks, because this is a theory of quark and gluons, to put the light quarks in these lattices, because the lightest the quark, the largest their Compton wavelength, so the large your lattice has to be. So the more, the larger your matrix is in your computer, and then the cost, computing time. Moreover, there are a discretization effect, because there is a lattice spacing. So you have to recover the continuum limits, so denser and denser lattices. Then you have to generate stochastic gluon configuration according to the weight of the QCD. So this also costs a lot of resources. But the progress is, there are simulations with lightest and lightest quarks, and therefore lightest and lightest pions. Until now, I think that the lightest quark that has been put in the lattice is 40 MeV, so around 10 times what is the physical world. And for instance, I take as an example this low energy constant C1. This low energy constant C1 is expresses the so-called nucleon sigma term, which is nothing else than the value of the quark condensate, psi bar psi, inside the nucleon. Okay, it's value. This is measured in the lattice. Also, it can be measured in other, in the experiment involving pion nucleon scattering, for instance. Okay, so there are discussions about the, meeting point from lattice and phenomenology, and slowly they come to an agreement. So the progress is there, especially for the lowest dimension Lagrangians. We are arriving at some lattice predictions for these low energy constants. Once we will have lattice prediction for these low energy constants, we will take this theory and compute more complicated processes, not on the lattice, but as a perturbation theory using these values. So this is like, how to say, you divide the job. I mean, this, yes, this is in principle, yes. In principle, you could say we use the lattice not to compute the nucleon-nucleon or the trinucleon force. It would be too complicated. We use the lattice to compute the coupling constant of a field theory which describes the trinucleon coupling. with no phenomenological adjustment. That would be, in principle, a prediction of the QCD. So, and the calculation that you do with the effective theory, with those values for the low energy constant, would be indirectly predictions of QCD about the nucleon-nucleon force. This is a way. Also, there is, I have to say that even in the lattice, okay, there are simulation which, you see, which put nucleons in the lattice. Well, there are also nuclear lattice effective field theory, but I'm talking about lattice QCD. To put two nucleons in the lattice, you have to put 6 quarks in the right combinations of colors and flavors and so on. So investigate the evolution, the dynamics of these 6 quarks, so, and extract from this something which would tell you about nucleon-nucleon interaction. So also there are direct attempts to arrive, but for sure, if on the lattice the determination of the nucleon-nucleon interaction could be foreseeable, and there are simulations doing that, it's not possible to imagine, to compute, for instance, a large nuclei complete with a lot of emergent phenomena directly from the lattice. You have to build another language in that case. And hopefully these languages should be connected. No? There would be a transcription joining different, like you were suggesting, from the lattice to this effective theory, also from, let's say, microscopic nucleon forces and what happens in more complex nuclei. It's not the same names in different domains does not ensure that it is the same thing. Probably what you call a particle in some theoretical setting is not the same as what you call particle in another, for instance, ab initio. Okay, this is, but so, but it is very in the spirit of the effective theory. It is to simply compute, to be effective, so to build something which works better than a complex simulation in the lattice, to divide the job in different scales, so to say. So we were discussing the counting of the loops here, and for each loop there are 4 powers of soft momentum, and then there will be propagators of particles in these loops. For instance, here there is 1 propagators of pions. Propagators of pion is I over p squared minus m pi squared plus I epsilon. Okay, this brings down 2 powers of soft momenta. Okay, because there is a p squared here in the denominator. Okay, you would say there is also m pi squared, but remember that p squared and m pi squared are of the same order. Okay, so they are homogeneous in this case. Twice the number of internal boson pion lines. Okay, internal pion lines. Then there are also nucleon propagators. Nucleon propagators. Here there is a nucleon propagators. In nucleon propagators is like that: I over p minus mn plus I epsilon. This is the nucleon propagator. And you cannot immediately say that it is there is this large mass of the nucleons. It's not the same as this m pi. Here, with the nucleons, there is the contribution of this large nucleon mass. So you have to cope with this somehow. And you can do this, okay, by saying that your momentum of the nucleons, your momentum of the nucleons is equal to m times the force velocity plus some soft momentum. Okay, don't have time to discuss very much. This is the so-called heavy baryon projection. Okay, with the and this is the form velocity. For instance, in the nucleon rest frame, this velocity is v mu is 1, 0, 0, 0. So the nucleon momenta in the nucleon rest frame will be a bulk of for momentum, mass times for velocity, plus some soft contribution given from impinging pions, for instance, or external sources. So the momentum of the nucleon will not be soft, but will be softly different from this bulk. Okay, this is. And you see, the nucleon propagator, so remember that this for velocity is equal to 1 v mu is equal to 1. So you see that the nucleon propagator p slash minus m nucleon, you multiply in the usual way like that, mn, and then in the denominator you have p square minus mn square plus I epsilon. Instead of p square, I express it in terms of this soft momentum given by other particles. So this p square is equal to m v mu plus soft k square, and this is equal to m nucleon square. Okay, I forgot the n. Here is the same mass, m square, plus twice m nucleon v dot k plus k square. And so you see that this contribution of the large mass cancels. Okay? So we have that the nucleon propagator is equal to I p slash plus mn over twice mn divided by v dot k plus k square over twice mn plus I epsilon. Okay? This is the expression of the nucleon propagator, expressed in terms of soft momenta, k. P is not soft, k is soft. So you see that k squared is much smaller than k, because k is a small number. So in the first instance, we can forget about this kinetic recoil, let's say, okay? And discover that the nucleon propagator scale like 1 inverse power of soft momenta, okay? 1 inverse power of soft momenta. In the numerator, you have this thing is projector of the, let's say, positive energy component of the nucleons. But the truth is that the nucleon propagators bring down not 2 powers of soft momenta, like in the boson case, but only 1 pion. Sorry, only 1 power. Okay, so minus I. Okay, each nucleon propagator. So this is v dot k plus, this is order p to the minus 1. So each nucleon propagators bring down 1 inverse power of soft momenta. And then there are the vertices. As usual. This di is this number. Okay, the chiral power, the number of derivatives, for instance, or depends on the number of quark masses. So this di is the chiral dimension of the vertex of type I. And there will be ni vertex of this type. A vertex of type I comes from some Lagrangian. If it comes from L1, this di is 1. If it comes from L2, it is 2, and so on. Okay, so this is the chiral power of the vertex. Then we have to use the topological relation. Topological relation. So there is a number of vertices minus I plus 1, perhaps. For instance, in this case, there are two vertices. No. For instance, in this case, there are 1, 2, 3, 4, 6, 7. 1, 2, 3, 1, 2, 3, 4, 6, 6. I always forget. I minus number of vertices plus 1. There is this topological relation relating number of internal lines in a diagram with number of loops and number of vertices, V. And this doesn't distinguish between internal lines of boson or internal lines of fermions. It's only topological. Then we have to substitute here. So we have 4 times L minus. So you see, you have that number of internal pion lines is equal to number of loops minus number of internal nucleon lines, and then plus number of vertices minus 1. So we have to retrace minus twice of this combination, plus V minus 1. Then we have to subtract number of internal nucleon lines again, and then we have the contribution from the vertices. This is the chiral power of each diagram with L loop and IN internal nucleon line. We can simplify this a little bit. Twice L, then there is plus number of internal nucleon lines minus twice the number of vertices plus 2 plus the vertex contribution I. Okay. Then we can also use another topological identity, which is the following. If you count the number of internal nucleon lines, double this number, and add the number of external nucleon lines, then this is the following thing. It is related to the number of nucleon fields appearing in the vertices of type I. You see, each internal line is attached to 2 vertices. Then this factor 2. Each external line is only attached to 1 vertex. Okay? If you count all possible vertices, okay, then you have this equality, okay, where Fi, I repeat, is the number of fields, fermion fields, appearing in the vertices of type I. For instance, in all these Lagrangian, the number of nucleon fields is 2, because n bar n is 2. Also here, okay, this F counts the number of vertex line. It doesn't count, for instance, one contribution to this diagram would be a 2-loop diagram like that to this self-energy. Okay, this is a purely boson, purely pion vertex with no nucleon. So in this case, F for this vertex is 0. Okay, if there are 2 nucleons, F is 2. If there are 4 nucleons, it is 4, and so on. Okay, so we can combine this information here to discover that the generic diagram will scale with soft momenta like that with twice the number of loops plus IN. IN I express in terms of n Fi over 2 minus En. So plus minus En, number of external nucleon lines, plus sum over I n I fi half. Then I have to proceed. There is this minus 2 here, minus twice the number of vertices. The number of vertices is the sum over all the ni. Then there is a 2 here, and then there is the chiral dimension of each vertices, ni di. Okay, so this is the chiral power. Let's bring some order here, plus twice my en plus sum over I, the number of vertex of type I times di minus 2 plus fi over 2. Okay. This is the scaling in soft momenta of a generic vertex involving En external nucleon lines. For instance, in this case, the number of external nucleon lines is 2, 1 and 2. Okay? The number of vertices, there are 2 vertices of type 1. Okay, so in this case, n1 is equal to, and there is 1 vertex of type 2. Okay, type 1, type 2. This, for instance, can be a vertex like d pi, pi, coming from the pi leading order pi Lagrange. Okay. So this chiral dimension is the following. So this number, di, I have to sum over I, runs between 1 and 2, okay, n1, so 2 times the number of derivatives in the vertex of type 1. Which was the vertex of type 1? This was coming from this Lagrangian, okay? So this d1 is equal to 1 in this case, minus 2 written here. And then the number of nucleon fields in this vertex we discussed before. Number of nucleon fields is 2 in this case. 2 over 2 is plus 1. So this bracket is 0, okay, for this diagram. Why? Because all the vertices are from leading order Lagrangians. Okay? And the same happens for the vertex of type 2. There is only 1 of them. In that case, the number of derivatives in this vertex is simply 2 minus 2 plus 0, because there are no nucleons in this nucleon fields in this vertex. So this is again 0. Okay? So the chiral dimension is simply twice the number of loops, in this case 2, so 4, plus 2, 6, minus number of external lines, 2, so it is order P4, these diagrams. Okay, this is clear. And this establishes the low energy counting of all the diagrams, which, okay. Now, the possible, the low energy expansion, so the fact that more and more complicated diagrams are less and less important, and so at some point we can neglect them, okay, depends on a single fact. The fact that this bracket is always larger than 0, okay? And this is basically because the pions couple derivatively. This is the same thing as we saw in the pion-pion sector. Also in this case, there is the addition of this characteristic Fi, but it makes that this is always larger than 0. This is, if you want, consequence of chiral symmetry, and then allows to establish the low energy expansion. We have to come to then after including extending the framework from the pions to one nucleon, then we have to extend the pions to more nucleons, okay, more nucleons. I have a small time, but this is, of course, the most important aspect. You might wonder why we didn't start from the beginning, from the case of 2 nucleons. And the answer is that the setting in the many nucleon sector includes the 0 nucleon sector. It includes the 1 nucleon sector. There is only an effective theory valid for all sectors. And this is, if you remember the first lecture, when we talked about what is a theory. A theory, with respect to some model, has a larger scope. The scope of this effective theory is not limited to 2 nucleons or 3 nucleons, but it connects these different sectors, relates the 0 nucleon sectors, Goldstone-Boson sector, with 1 nucleon sectors, for instance, pion nucleon sigma term, 2 nucleon sector, okay, in a single setting. We can use the information from one sector and transfer in the other sector, because there is no point in starting directly with the 2 nucleon sector, because in the 2 nucleon sector, when, for instance, we have 2 nucleon lines like that interact through the exchange of a pion, this is the Yukawa potential, okay. What enters here is the vertex that we have discussed before, which comes from the 1 nucleon sector, okay. So this coupling constant is the GA over, we have written, no? F pi, okay, F over pi, then, okay, this brings to well-known Yukawa interaction. So it is a prediction, because this GA is known, this F is known. GA is 1.27 from the axial structure of the nucleon. F is 92 MeV from the pion decay to the muons, you see? Then this is a prediction of this framework, a prediction. The large distance behavior of the nucleon-nucleon interactions, okay? It's dominated by the pion tail, okay? This the potential. You can compute these Feynman diagrams. It is quite simple. There are 2 powers. Sorry, this is 2 for F squared. If this is momentum, nucleon with momentum P1 and momentum P2, scattering with momentum P1 prime, P2 prime, okay. So these pions has the momentum transfer P1 minus P2. In terms of this momentum, this is sigma 1 dot Q, sigma 2 dot Q, tau 1 dot tau 2 over Q square plus m pi square. Okay, this is the computation of this Feynman diagram. Okay, it involves the nucleon momentum transfer. So Q, recall, Q is P1 minus P1 prime. Okay, P1, okay, so if you Fourier transform, this is the potential, let's say, in the momentum space. If you Fourier transform this, you get the Yukawa potential. This is quite standard, and I presume that is familiar to you. Okay, so, but in addition, when you consider more nucleons, there are more ingredients. These are only ingredients involving 1 nucleon at a time. Okay, there will be more ingredients in the case of 2 nucleons. for instance, there can be interaction like that. Is this chiral invariant? Yes, it is. Why? Because remember, this scale like n bar goes into this h dagger h n bar h dagger h n. So and this is unity. This is unity. So it is allowed. It is a possible term of the effective Lagrangian. It will involve 4 nucleon fields, 4 fermion fields. In this case, the number of derivatives of an interaction like that is 0, no derivatives. So this is minus 2. Plus, there are 4 nucleon fields. So this F is 4. 4 by 2 is 2. So this square bracket is again 0. Okay, so this is, and this does not spoil. What will spoil is other features that we can discuss in the afternoon if you wish. Okay, so there is a term like that. This is allowed by symmetry, by chiral symmetry. There are no constraints from chiral symmetry on terms like that. They will involve a completely free low energy constant. People call it CS, okay, CS. It is not the only possible term. Also a term like that, n bar tau a n bar tau a n is perfectly allowed by chiral symmetry. Okay, if you sum over a from 1 to 3, this is allowed. You have the tau short distance interaction, or you have the sigma I n bar sigma I n interaction, or you will have sigma tau, okay, both n bar sigma I tau a sigma I tau a. Notice the way I combine the isospin and spin indices, so to make isoscalars, okay, or scalars and rotations. Why? Because we want to preserve the isospin symmetry, which is part of the chiral symmetry after all. Okay, so this saturation of the isospin index is a requirement of chiral symmetry, okay, of a subset of chiral symmetry, which is isospin symmetry. This saturation of the spin indices is a requirement of rotation invariance. Okay, so you can have short distance structure which are depicted diagrammatically like crosses in this way. They represent 2 nucleon interactions parameterized by some low energy constants, okay, which include in their magnitude a short distance effect, like for instance exchange of particles heavier than pions, for instance rho meson or heavier mesons. Okay, in the effective description, like it was the case for the W exchange from the standard model to the Fermi theory, the diagram shrinks to a contact interaction, and the effect of these heavy mesons go in the value of this low energy constant, CS, or this is CT, CS, CT. There are no constants attached to these interactions because of the symmetry. Okay, I unfortunately cannot discuss this in a few minutes, but because I want to arrive to the hierarchy of the nuclear forces. These nucleons are identical particles, so they satisfy the Fermi symmetry. If you interchange, you pay a price. So if you exchange the indices of space and isospin, because they are at the same point, this point. So if you wish, the Pauli exclusion principle forbids, relates interaction that I have barred here with the two ones. There are only two at the end, okay? Which traditionally are called the CS and CT, okay? This interaction and the spin-spin one. The others are related by fierce relations among each other. Okay, this is for two nucleons. This is just these two diagrams make the leading order nucleon-nucleon potential. Okay, the next to leading order nucleon-nucleon potential is obtained by adding loops, okay, or by adding derivatives. Derivatives. For instance, we could consider a diagram, one panel exchange diagram, with vertices not from L1, but vertices from L2, okay? This will be a sub-leading contribution to the nucleon-nucleon amplitude, okay? So let us see if there are normally vertex with from sub-leading Lagrangians are with a square or something, okay, to distinguish. Let us look if there are nucleon-nucleon pion interactions coming from L2, which would yield sub-leading contribution to the same mechanism. The answer is no, there are not, okay? Because here there are always two pions contributing. Two pions contributing. Remember, this u mu is at least linear. Two pions contributing. Here, also, in the isospin limit, there is combination u cross plus u, which involves at least two pions. All this is involving at least two pions. So there is no contribution which is suppressed by one order. Okay? The next order involves two extra powers of soft momenta. So the first contribution is of order P0. Just count the powers of momenta. 1, 2, minus 2. P0. This is the first contribution. Okay, this is simply CS, the contribution in momentum space, or CT, sigma 1, sigma 2, in momentum space, unity. So again, P to the 0. In coordinate space, it will give delta function, interaction with a delta function, short range interaction. Two nucleons participating at the same point. Okay, it should be regularized and the like. But there is no contribution at next to leading order, I mean at order P suppressed relative to this. This is 0. The next contribution comes from order P squared. It will involve one loop diagram, okay? One loop diagram. For example, just to use vertices that we already met, okay, this is the Weinberg nucleon pion vertex, and this is the axial pion-pion nucleon coupling. This will contribute to the nucleon-nucleon potential at order P squared. Normally, this is called next to leading order, okay? There is a jump of momenta from leading order and next to leading order. They are different by 2 powers of soft momenta. Okay, then in addition to this, there are also contact interaction with dimension 2. It means with 2 powers of nucleon momenta. For instance, it could be like that. So it's a rotational invariant nucleon-nucleon contact interaction, invariant and yes, with 2 powers of momenta. So order P squared, also this. You have to classify all possible combination, okay, of rotational invariant, parity invariant, all the discrete symmetry, isospin invariant operators, which contain 2 derivatives. Okay, people have done this, and there are there are 7, okay, 7 low energy constants. Traditionally, they are called C1, C7. These are low energy constants that are taken from experimental data, from the fit to the nucleon-nucleon phase shifts. Okay, and this is also a part of the contribution at next to leading order. What is the use of a potential next to leading order is that, with respect to the leading order, it is more accurate. Why it is more accurate? Well, perhaps because we have simply 7 more parameters to adjust to experimental data. No surprise. Okay, surprise. Yeah, this is inevitable. Then the, next to leading order, okay, next to leading order, which is order p to the cube, 2LO, okay. Perhaps there are the contribution of one loop, okay, where one of the vertices is not from L1, but it is from L2. So we put a cross, a square there, not to distinguish. Not there. So this is a contribution of, and we don't have extra legs because this square, subleading pion-nucleon interactions, we take it from the pion sector, okay? We take it from the pion sector. There is a difference between the vertices involving pions and the vertices not involving pions, like this C1, C7. Those we have to resort to nuclear data to determine. The vertex with the pion, we can take it from the one nucleon sector, okay? So the terms which enable us to construct accurate nucleon-nucleon potentials are the contact interactions. There are 2 at leading order, CS and CT. There are 7 at next to leading order. Sorry, at next to leading order. And then there are terms at following order, N3LO, N3LO. Order P4. There will be, let us put here a triangle, cross diagrams, contact diagrams, with not 2 powers of soft momentum, but 4 powers of soft momentum. Notice that the number of derivatives must be even because of parity. Okay, so must always be similar. Here we have additional freedom, additional low energy constants, parameterizing this kind of interactions, okay, containing 4 powers of momenta. These low energy constants are traditionally called D1, and there are, recently it was found that there are 17 of those in the general reference frame. 17 of these low energy constants. So number of low energy constants increases, and the accuracy, consequently, of the potential also increases the more you proceed with the orders. Except that these 17 low energy constants in the nucleon-nucleon rest frame, or if you like, there are only 12 contributing, 12 combinations. I mean, some of these contributions change the off-shell behavior of the nucleon-nucleon pair. So they cannot be determined from experiment. So actually there are 12, only 12 of those which can be determined. So at leading order we have 2 handles to adjust our potential. At next to leading order we have additional 7, so in total 9 low energy constants. At N3LO we have 9 plus 12, 21 low energy constants. And at N3LO, people have developed the potential that give a chi-square over thousands of nucleon phase shifts, scattering phase shifts of order 1. So they become realistic potential at N3LO. Like phenomenological potential, like AV18, for instance. The difference is that in some sense it is microscopic. Also, you could say that they become realistic simply because you have more parameter fit, okay, to adjust. But notice that this number of adjustable parameters with respect to the AV18, phenomenological AV18 or CD bond, or other nucleon-nucleon potential, is much less, almost half of the parameters in the chiral potential compared to the phenomenological accurate potential. So it is a more predictive framework. Especially, it gives indication of what is left out, okay, of the size of the neglected orders. So it gives indication about the uncertainty. I fear that I have to stop here. I told you much less than I had foreseen, but there is the discussion session. I wanted to discuss especially 3 nucleon force and explain why they are smaller than 2 nucleon force, the hierarchy of nucleon force. I didn't have the time. So if this is a question, for instance, from you, we can discuss in the afternoon. Otherwise, let's stop here.